It is my pleasure to introduce Alex Koszegi. Alex is a senior solutions architect at D-Wave, working with clients to identify, develop, improve, and benchmark their applications using quantum hybrid technology. Alex was here last year as well in the WOMANIUM quantum program. Then she still had another role. She was a sales engineer, identifying opportunities for using quantum in clients' business applications. And her story at D-Wave has been longer. She actually started there as a service and support team member, installing quantum processors hands-on and also supporting users to use the D-Wave cloud platform. So Alex's experience is really vast, from the hands-on part to working with clients. You have a bachelor in electrical engineering from the University of Victoria, and we really look forward to you sharing everything about quantum annealing with us today. Thank you for being here, Alex.
Thank you so much, Marlou, for having me back. It was a lot of fun last year, and I'm excited to be here this year. We also have Catherine Potts on the line. So you'll hear more about her background and her expertise tomorrow, but she will be running the software boot camp. So it'll be kind of an extension to what we're looking at today. But yeah, all right. Well, let's dive in then. Thank you so much to everyone for joining the session on quantum annealing. I always enjoy giving these talks because now that I'm so client facing, I'm working a lot with industry applications. It's fun to get a space to kind of nerd out on the hardware. So thank you all for giving me this opportunity. So today we are going to start by talking about D-Wave. I'm sure many of you already know about D-Wave as a company, but I'd like to give a bit more background on kind of where we started, the technological advancements we've made along the way, where we're at today, and where we're going, just to kind of fill in that context for you all. We'll talk about a couple applications that are in production today. This is kind of setting up a high-level motivation as to why annealing is interesting and why so many folks are starting to explore it, not only for research, but also for business. And it also kind of lends itself well to the session that Catherine will do tomorrow, which will be much more hands-on and focused on using the quantum annealer instead of learning about how it works. So after that, we'll talk about what quantum annealing is as an algorithm. We'll talk about how we build a quantum annealer. And then I have a couple videos for a lab tour to show you. Unfortunately, I can't go into the lab today, so it won't be live, but the videos hopefully give it justice, and it'll give you a sense of what our lab looks like. Oh yeah, and then at the end, we'll do Q&A. So yeah, please hold on to your questions and we'll have a chance to discuss. Okay, so D-Wave has been around for a very long time. I'm sure many of you know this, but we were actually founded in 1999. So we're quite ancient, and we might even be one of the first quantum computing companies out there. So in 1999, when our founders first came together to start a quantum computing company, there really wasn't a lot of research, and there wasn't a clear idea on how you might build a quantum computer, like a universal quantum computer. This was very much a theoretical idea still. There was research, though, starting to come out that suggested there might be a way to build an adiabatic quantum computer, especially with superconducting qubits. So our founders thought, well, there's this research that we can kind of leverage. We have some idea of how we might do this. And we know that adiabatic quantum computing, there was some other theoretical work suggesting that it could be really useful for certain classes of problems and for optimization problems. Now, right from the beginning, we've been focused on a path towards commercialization. So this decision to start with a quantum annealer so that we can address a wide variety of problems across industries really was in line with this vision of one day delivering commercial quantum computing. So for the first 20 years, we spent that time developing a strong technical foundation in quantum chip design, in cryogenics, in calibration, all of these technical components that we need to build a large, scalable, well-functioning quantum annealer. And this led us to releasing our first commercial quantum computer in 2011. So at this point, I believe it had 128 qubits. It was mostly the national labs and the research institutes that were interested in purchasing and using the quantum computer for research. But since then, we've continued to iterate on our technology. We've continued to learn, to expand, to scale. And in 2017, we released our 2000 qubit quantum processor. So at that point, the processor was starting to get large enough that we were able to do some interesting things. I'm not going to talk about these milestones on this slide because we'll talk about a few really important ones on the next slide. But from 2011, really until today, we've proven to ourselves a number of kind of milestones, or hit a number of milestones along the way, suggesting that we are on a path towards commercialization and suggesting that there are real world problems that could benefit from quantum annealing. So it's been a very exciting journey. If we fast forward to today, we have our current quantum computing system called Advantage. Advantage has over 5,000 qubits. And what's really kind of interesting about Advantage is that it's now at a scale where it can support what we call hybrid solvers. So hybrid solvers utilize classical and quantum resources to address larger industrially relevant problems. So it's through our hybrid solvers that we're actually able to start applying quantum to real-world industrially relevant problems today. We're hearing from our customers, and you'll hear a couple case stories a little bit later, that they're seeing business advantage from using our systems. So we're really quite inspired by kind of where we've gotten, and we're feeling optimistic about where we're going with our quantum annealing systems. So if we look ahead to the future, we're going to continue developing our quantum annealing systems, continue expanding on them. We have layouts for the next 2 systems already kind of on the works. So we have a vision moving forward on the quantum annealing side, but we're also starting to build a gate model quantum computer. So eventually, when we get to a point where we're able to release that technology, and it's still a long ways out, you know, that doesn't happen overnight. But at some point, we'll be at a point where we'll be the only company that has both gate and quantum annealing computers. So we're really excited about kind of the direction that we're going in. Now, that being said, to get to this point, it's taken a lot of work. And we've needed to really vet our technology and hit a number of key milestones to make sure that our technology is both scalable and useful in the ways that we want it to be. So I mentioned that for the first 20 years, we were kind of building out a strong technical foundation. But on the research side, up until 2015, that looked like focusing a lot of our kind of published efforts or our public-facing efforts on sharing with the world what quantum devices we were using, how we were building a processor, how the quantum dynamics were emerging in our system. You know, we were really working on understanding that and sharing that more broadly. So in 2011, we were able to demonstrate that our processor relies on quantum mechanical effects, primarily tunneling, for ground state computation instead of thermal effects. So this was kind of the first demonstration of using primarily quantum dynamics in our system as opposed to thermal. In 2015, we released a paper that showed experiments demonstrating entanglement on 2 and 8 qubit systems. Those are smaller systems, but that experiment was quite involved. So to scale beyond that would have taken a lot of effort. In the last couple of years, though, the more recent work that we've done kind of requires that entanglement exists on a broader scale in the processor. Otherwise, we wouldn't see the results that we've seen. So since 2015, we've also kind of verified that entanglement is present for certain problems in our processor on a much larger scale than an 8-qubit system. After 2015, we kind of shifted focus in terms of where we were focusing our public-facing research efforts. And we started to ask the question of how can we use this quantum system that we've built to simulate other quantum systems? So, kind of continuing along the same vein or the vision that Richard Feynman had. And so from 2018 to 2011, we performed a number of simulations on magnetic materials. So first we looked at simulating second order phase transitions between paramagnetic, antiferromagnetic, and spin glass phases. So that was in our first 2018 paper here. And that worked with a 8x8x8 qubit lattice. After that, we observed a KT phase transition in an 18-qubit lattice, or 1800 qubit lattice, sorry. Beyond that, we were able to simulate a quantum system with quantum annealing and show a speed up of about 3 million times over a quantum Monte Carlo algorithm. So that was in 2021. And the relevance or the importance of these three pieces of work is that they demonstrate that we're able to simulate quantum dynamics, quantum systems with our quantum computer. And there's lots of evidence suggesting that the simulations that we performed here we're not able to perform them classically. So we're really utilizing the quantum dynamics, the quantum nature of our system to investigate these materials and investigate these quantum phase transitions. This is also interesting to us from the perspective of it can further research efforts in condensed matter physics and quantum magnetism. So there are still some applications, although they are a little bit more on the research side of things that can come out of the work that we did at this period of time. In the past couple of years, we've shifted our research efforts a little bit. We've still built on the simulation work, but have gone in more of a direction of demonstrating coherence on different size systems. So last year, we demonstrated coherent quantum annealing on a 2000 qubit Ising chain. And this year, we released a paper showing a coherent quantum annealing on a 5000 qubit spin glass. And what's really exciting about this research is that it's the first research papers published that we know about that shows how experimental data from our quantum computer or quantum annealer, how it agrees with theoretical models for coherent quantum annealing. So again, the last 10 years has really been about strengthening this theoretical foundation, understanding how our QPU can be used for simulations and understanding quantum materials, and kind of proving out and understanding where technology is so that we can scale and continue to go in a direction that is relevant for solving other more broad optimization problems in industry. Okay, we've talked about a lot of theoretical work, but I'm sure you all have a question as to what does our quantum computer look like? What is this thing that I'm calling Advantage? So we'll see an older version of our quantum computer in the lab videos, but this is an image here on the slide of Advantage. It's a big box. And our QPU lives inside of this big box here. So this is an 10 foot by 7 foot footprint. So it's quite large. The larger chamber here houses the cryogenic system and the QPU. And then we have 3 racks on the front. So we have our server rack that connects the QPU or the system to the outside world. So when you use it on Leap tomorrow with Catherine, what you'll actually be doing is interacting with this server rack that lives on the quantum computer. We have other racks for controlling the room temperature electronics and the electronics that send signals down into the QPU, and pumps for ensuring that the cryogenic system is operating at the 12 millikelvin that we need it to. So that's what our quantum computer looks like as a whole. Now, the Advantage chip, I already mentioned that it has over 5,000 qubits. And this is really big in the quantum computing world. But remember that we're focused on commercial applications. So that's kind of the framework that we're evaluating our technology through, at least from my perspective, being on the customer-facing side. So although 5,000 qubits is a lot, it's still not quite enough to apply to real-world problems in a meaningful way. However, it is enough to kind of plug into our hybrid frameworks so that we can utilize classical and quantum resources to start to address these larger industrially relevant problems. So we have a couple different hybrid solvers called the constrained quadratic model hybrid solver and the binary quadratic model hybrid solver. These hybrid solvers essentially just work with different math models at their base. The BQM, or binary quadratic model solver, is a little more closely tied to the Ising model or the underlying chip in terms of the model that it solves. However, in industry, when we're solving optimization problems, we often have some quantity or something that we're trying to optimize, as well as a lot of rules or constraints that need to be satisfied for us to find viable solutions. And it turns out that these constraints are really difficult to model in a binary quadratic model. However, with our constrained quadratic model solver, they become very easy to implement and to satisfy. So when we're working with clients, it's the constrained quadratic model hybrid solver that we use most of the time. But the point here is just to say that we're able now to incorporate quantum annealing as part of a broader hybrid framework to address a variety of optimization problems. So then D-Wave as a whole, you know, we build and we deliver and we provide access to our quantum computers. That's kind of the heart of our business. We provide access to our quantum computers through a cloud service that we develop and maintain though. And that cloud service is called Leap. I think you'll get a tour of Leap from Catherine tomorrow. We have developer tools, so a Python tool set for building models, interacting with our hybrid solvers, interacting with our quantum computers, doing pre and post processing. So everything that you need to be successful in interacting with our systems, we provide tools to do so in Ocean, which is our Python SDK. And then we also have the launch program. So that's my team. We work with customers to deliver quantum hybrid solutions. So as a whole, this is kind of what D-Wave offers. This is the access that we offer. Yeah. Okay. So now I wanted to cover a few applications. But first I wanted to start with kind of a high level overview of a few different verticals that we're seeing a lot of interest from. So optimization problems are found everywhere, especially in industry. Many industries are interested in how to optimize their business processes, their manufacturing processes, any optimization problem that they have. If you can find a better solution to it, you're likely to affect their bottom line. And companies are very interested in that. So some of the main verticals we've seen so far are in logistics and manufacturing, in pharma, and in finance. However, that's just a subset of the areas where there are optimization problems that we work with. So this is just to give you a sense of kind of the breadth in which we can apply our technology to. Now, I wanted to talk about a couple of our production applications to again highlight the commercial element of our products and our services. So if any of you are in Canada, particularly Western Canada, you may have shopped at Save on Foods It's a grocery store. I was just there yesterday. But they're owned by Pattison Food Group. So Save on Foods, though, they are they try to implement very cutting edge technology. They're always looking for a business advantage, and they're looking to kind of provide new services to their customers to kind of satisfy them and cater to them better than other grocery stores. So in order to do this, a few years ago, they implemented next day delivery of food and health products in their stores across Western Canada and the US. And when they first started to do this, they started scheduling drivers and deliveries and orders all by hand. You can imagine they had 100 stores and over 500 drivers. So this was a big undertaking to do by hand. And the challenge of doing this manually is that you can't tell how good your schedule is. You know, how satisfying is it to your drivers? How good is it at meeting your business needs? These are questions that are very difficult to measure when you have a solution that's implemented in this way. So they were interested in exploring quantum at the time and understanding how they could apply quantum to deliver business value, and came to the realization that this would be a great use case. They worked with us on something else, and then they were able to develop this solution entirely on their own. So they built a program that they're calling the Quantum Hybrid E-commerce Driver Auto Scheduler. That's a mouthful. It's called QEDA. But essentially what it does is it looks at all of the orders that have come in for a day, everything that needs to go out the next day, and it pairs drivers with location-specific shifts. It also does additional things like it considers the preference that drivers have for certain shifts in certain stores. It uses drivers' seniority to rank those preferences. It considers labor laws. So drivers can only work a certain amount in a certain day. You can only work a certain number of days in a row in a 14-day window. So there are many constraints and many business rules that come into play for a problem like this. And with our CQM hybrid solver, they were able to handle all of their constraints. They were able to actually improve the schedules. So in the past few months, since this has been in production, it went into production in October last year, they've seen less driver turnover, and their schedulers are also more easily able to adapt to changing business demands. So if someone calls in sick, they're still able to meet the business needs and deliver the orders that need to go out that day. The next example that I wanted to give was of SavantX. SavantX is a startup in the States, and they look at applying machine learning, data analytics, and quantum computing to logistics problems. So a few years ago, they were working with the Port of LA on optimizing the port logistics. And through that initiative, they were able to develop a system they call HONE. And so HONE is an optimization engine. And essentially what it does is it looks at a shipyard. So whenever you have a cargo ship come in to a port, you have to unload all of the shipping containers into the shipyard. And it looks kind of like this, like in the image here. Then you have these rubber tire gantries, so these big cranes that have to move around the shipping yard because they're what loads the shipping containers onto trucks. And typically, these shipping containers aren't ordered in any particular way. They're just kind of placed in the order in which they come off of the cargo ship. So, and it's also very expensive and time-consuming to move these rubber tire gantries. So if you're just kind of doing this ad hoc and working through loading shipping containers onto trucks, as the trucks come in, you're moving these rubber tire gantries a lot, and it's very costly to the port. So by optimizing the routing of these rubber tire gantries, as well as optimizing the order in which the drivers were called to come pick up their shipping container, SavantX and their system were able to process 60% more cargo every day, which for a port like LA is a huge cost savings. So those are just a couple examples of some of the real world applications that are utilizing our systems. And I just wanted to kind of motivate or inspire kind of why quantum annealing is interesting, especially today, now that we're addressing industry problems. But now, let's talk about what you all came to learn about, and that is quantum annealing and the technology that we develop. So thank you for bearing with me for the first little bit while we set the stage. All right, so what is quantum computing? At its root, quantum computing is essentially an algorithm that uses quantum mechanical effects to find the ground state of a Hamiltonian. If you're a physicist, that probably makes a lot of sense to you. But if you come from a computer science background, it might be more intuitive to think about this as an algorithm that's looking for the global minimum of an objective function. However you think about this, it turns out that this process, this algorithm, is really well suited to solving optimization problems, because when we're classically approaching optimization problems, we actually model them and we think about them in a very similar way. So when we think about solving an optimization problem, we typically will construct an energy landscape, and we're looking for the lowest point on that energy landscape, which represents the optimal solution. So there's a lot of analogies between classical optimization techniques and quantum annealing. At the heart of quantum annealing, it relies on the adiabatic theorem, which says that if you have a quantum system that you initialize in some ground state of a Hamiltonian, and then over time, you slowly change that Hamiltonian into a new Hamiltonian, if you do that right, then you will end up in the ground state of your final Hamiltonian. So this is the idea of ground state computation. And if we look at these diagrams here, we can see one example of what this might look like. So for our systems, we initialize our Hamiltonian, or our QPU, into a very simple Hamiltonian that looks something like this. It just has one single global minima. That's it. Over time, we start to evolve this very simple system into a Hamiltonian that represents the problem that we're trying to solve. And so as we're evolving that Hamiltonian, you'll see additional features emerge in the landscape. Now, the idea is that the QPU is hanging out in this global minima, so here, here, and eventually here, while you're changing the landscape around it. Every point on this landscape represents, oops, where did my mouse go? There we go. Every point on this landscape represents a possible solution to your problem. And the lower energy the point is, the better quality the solution is. So ideally, you want to end up in the global minimum, because that represents the optimal solution, as long as you've constructed your Hamiltonian correctly. Now we can look at that 3D plot in a bit of a different way. So what we're looking at here is just a 2D representation of the 3D plot on the previous slide. And here, the black curve represents the energy function. So the black curve is analogous to the 3D plot. We have this blue dotted curve as well, and this represents the waveform, or the wave function. So the wave function tells us the probability of ending up in any particular state in the energy landscape. So you'll notice that in the beginning of the anneal, when we've initialized our system into a simple Hamiltonian, the wave function is localized around this global minima. So this is exactly what we want. This tells us there's a high probability that our quantum system is in the ground state. As we start to anneal, and our energy function starts to change, we see the emergence of multiple minima, we see the emergence of narrow barriers. And what happens to our wave function is that it delocalizes and spreads out over all of these little minima. So now there's a probability that, some probability that our quantum state is in a lot of different places. It's not localized anymore. As we continue through the anneal and the quantum dynamics slow, what ends up happening is the wave function will relocalize, ideally around the global minima. So here we have a high probability that our state, our QPU, is in this state here. Ideally, it's the global minima. And at this point in the anneal, what we end up reading out is just a classical state of spins. So a classical sequence of spin up and spin down. At this point in the anneal, there are no more quantum effects at play, and it's essentially a classical system. Okay, so you can represent this process with a math model called the transverse field Ising-Hamiltonian. So here we've kind of talked about two distinct components to quantum annealing. We have this initial state, and then we have this final state, or the problem that we're trying to solve. And so if we look at the model of this, we see that both of those states, they correspond to different terms in the Hamiltonian. So this first term here that operates on sigma x is our transverse field Hamiltonian. And this is responsible both for the quantum effects that are at play. It applies the quantum dynamics. You can think about it that way. But it defines the simple Hamiltonian that we start with. So this is our initial Hamiltonian defined by the transverse field. Through our anneal, we start to combine these two components to our two components of our Ising-Hamiltonian, so the transverse field and the problem. And then by the end, the energy landscape is fully characterized by the second component of the Hamiltonian. So that is the problem Hamiltonian. And here you'll notice that the problem Hamiltonian, it only acts on the sigma z terms. The h's and j's here are what are user defined. So these are biases on a single qubit, that's the h, and the j's are a bias on pairwise qubits. So they essentially represent the strength of a relationship between two qubits. And the h's and j's are what emerge from our problem domain. So when we formulate a problem, this is what we're trying to figure out, or what we're defining, so that we can send those to the QPU, and that ends up defining the problem. So you'll see an example of that tomorrow in Catherine's session. All right, so there's still one component missing to this kind of idea of quantum annealing. We have the general idea of how it works. We have this math model, but we also need some type of schedule to define how the system evolves over time. And we have what's called an anneal schedule that defines that. So here we're looking at a plot that on the x-axis has the normalized anneal parameter. So this parameter goes from 0 to 1, and it represents the duration of an anneal. The actual amount of time that this takes, it can change. By default, we set this to 20 microseconds, but as a user who's submitting a problem, you can change that between, I believe it's 0.5 microseconds and 2 milliseconds for advantage. So you can really play with that range. On the vertical axis, we have the energy. So this is the strength at which each of these terms is turned on. That's how you can think about it. This blue curve here represents the initial Hamiltonian, or the transverse field, so this A of S term. And this green curve here represents the problem Hamiltonian. So you'll notice there's a fixed relationship between the magnitude of the initial Hamiltonian and the magnitude of the problem Hamiltonian at different points along the normalized anneal parameter. And this relationship is fixed. The system just moves kind of through the schedule. So at the very beginning of an anneal, we've mentioned that we initialize the QPU in a very simple Hamiltonian. And so what that actually looks like is all of the qubits are in superposition. So the full contribution from this initial Hamiltonian is kind of the quantum contribution, as I mentioned. When it's fully on, all of the qubits are in superposition and they're not impacted at all by the problem, because we can see that the problem Hamiltonian here is at 0, it's completely turned off. As we start to progress through the anneal, we start to slowly turn off the transverse field, and we start to slowly turn on the problem Hamiltonian in this fixed relationship. As we get close to this crossover point, though, where the problem Hamiltonian becomes stronger than the transverse field, this region is particularly interesting because it's where most of the quantum dynamics are performing on our problem. So they're contributing to finding a solution, a good or the best solution to the problem that we're trying to solve. And then after this point, our qubits start to freeze out. So what that means is they collapse from a quantum state into a classical spin state of spin up or spin down. And then once we get to the end of the anneal, all of the qubits are in a classical spin state, and we can just read out the state of those qubits. All right. Oh yeah, okay, one more thing. So now that we've talked about how quantum annealing kind of works on the global processor level, I want to zoom in to how it works on the individual qubit level. So we can characterize an individual qubit by a double well potential. This is the energy function for a single qubit, and each well here represents the possibility of the qubit ending up in spin up or spin down. And we can also map this idea of spin up and spin down to binary variables as well. So yeah, there's a mapping there that we often use. Now this barrier here, or you can think about this as a barrier, it's what separates the two wells. So it tells us that we have a distinct possibility of ending up in spin down or spin up. And the height of this barrier is what corresponds to the transverse field. So while we're annealing this transverse field, it's actually raising this barrier. When this barrier is all the way down at 0, our qubits are in superposition. So that's the beginning of the anneal. And then as we progress, we raise this barrier to create these two distinct states. And the qubit has to decide by the end of the anneal which state it's in. Now, I said that the user can define a bias on the qubit. And this bias tells us if the qubit prefers to be in spin up or spin down. That's the H value in the Ising Hamiltonian. In terms of the double well potential, what this H value does is it essentially just tilts the potential so that it favors one side or the other. So in this example, we can see that the spin up state is lower than the spin down state, which means that this qubit prefers to be in spin up. The last element of our Hamiltonian here is the J term, or the quadratic term on two qubits. And this J term, it defines a relationship between two qubits. So it'll say these two qubits either want to agree, they want to have the same state at the end of the anneal, or they want to disagree, they want to have different states. So we can program kind of a range of strengths of that, that type of relationship of agree or disagree. Okay, so now that we've talked about the idea of quantum annealing, let's talk about how we actually build a processor. So one way to think about our qubits, well, I should first start by mentioning that our qubits are RF squids. But one way that you can think about an RF squid is as just a superconducting loop of wire. Now, superconductors are really important in quantum computing because they have a couple properties that we can exhibit or we can harness. So the first is that when a superconductor is cooled down past a certain temperature, so past its critical temperature, it it starts to change and exhibit different properties. And one of those is that it has zero resistance. So if you have current circulating through a superconductor, there's no resistance in that superconductor, which means there's no heat dissipation, which means that it's not adding noise to our system. And with quantum systems, especially when we're using them to solve problems, that it's really important that we keep the environment as noise-free as possible. The second property of superconductors that we harness is that if you have a loop and you're circulating current, when the metal is superconducting, you actually get current circulating in both directions at the same time. It's a very interesting property of superconductors. Now, for us, we use these loops of wire as our qubits, but the state of a qubit, the spin up or spin down, the way we realize that is through the direction of the magnetic flux through the body of the qubit. And you might remember from an E&M course, the right-hand rule. So this tells us that the direction of the current circulating in the qubit tells us the direction of the flux through the center. So it's either up or down, depending on if the current is circulating clockwise or counterclockwise. Now, when you have current circulating in both directions, you might think that the flux cancels out, but it actually doesn't. You get flux traveling in both directions through the body of the qubit when you use these superconducting loops. So this is how we create this state of superposition. We use a superconducting loop. We allow current to circulate in both directions. This creates magnetic flux traveling in both directions through the body. So that, yeah, this is how we create superposition. Now, if we only had a loop of wire like this as our qubit, we would be stuck in superposition forever. We wouldn't be able to get to that state at the end of the anneal where the qubit has to decide if it's in spin up or spin down. So the way we change that is we introduce a little break in the wire. We fill it with a dielectric, and we call this a Josephson junction. So when we do this, we actually get some current passing through this Josephson junction, and the maximum current that can pass through is called the critical current. Now, this Josephson junction here, what it enables us to do is create a barrier. So it allows us to go from that single well potential into a double well potential. And the magnitude of the critical current, it dictates the height of this barrier that we looked at in the double well potential. So this is great. We can now create a qubit that has two distinct states. But the problem here is that if we only represented our qubit this way, now we would be stuck in this double well potential state. So next, we need to figure out how to go from a state of superposition to the state of a double well potential. And the way we'll do that, so essentially what we're trying to do is create a tunable qubit, is we replace the single Josephson junction with a loop that has two Josephson junctions in it. And when we do that, this allows us to actually change the height of this barrier to tune it. So we can start the anneal with this barrier height all the way down at 0, and then over time, we can apply a magnetic flux to this CJJ loop, and applying that flux will raise the barrier height. Applying a flux to that loop, it essentially changes the critical current through the Josephson junctions. So that's how it kind of physically ends up tuning that barrier height. We also have that bias that acts on a single qubit. And the way we physically implement that in the chip is that we apply a flux to the body of the qubit. And the magnitude and the direction of this flux tells us which direction or which state the qubit body is biased towards. Now, the last thing we need to implement, at least in this simplified model that we're talking about, is our coupler. So we need a way of encoding relationships between qubits. So the way we implement a coupler is we use a qubit-like device. The coupler is here in red, and you might notice that it does look pretty much the exact same as our qubit. It is a similar device, but the parameters are different so that it has a monostable energy function. And the way we use this is we apply a flux to, again, the CCJJ loop here. And what that ends up doing is it then creates a mutual inductance between the coupler and the two qubits on either end of it. So the magnitude of this, my mouse keeps disappearing. The magnitude of this phi CO is what determines or what ends up translating to the J value that we decide we want to apply to a set of qubits. And the way it translates is through this plot here on the right. So you'll notice on the x-axis, we have phi CO over phi naught. So this is just the flux that we're applying to the CCJJ loop. And then along the horizontal or the vertical axis, we have the mutual inductance. So if we operate our coupler in this area or in this region up to, it's about like 0.5, here, what we end up creating is a positive mutual inductance, and that corresponds to an antiferromagnetic relationship between these two qubits. So that means the two qubits want to disagree. If we increase the flux through this body just a little bit more, then we can end up pushing the mutual inductance into the negative range. And once we do that, we're able to create a ferromagnetic relationship. So that means both qubits want to agree. They want to have the same state at the end of the anneal. So by changing the magnitude of this flux that we apply to the coupler, we can change the type of relationship that we're applying to the two qubits. And this is essentially how we realize this J value that the user defines in their problem. Okay. So now that we know at a simplified level what our qubits look like and how we create couplers, we can use those building blocks to build a full processor. And the way we do that is we start by building tiles of qubits. So in this image here, each loop here represents a qubit, and each dot represents a coupler. So you'll see, so that's a qubit. And then the couplers or the dots where the horizontal qubit intersects with the vertical qubits represent this horizontal qubit being coupled to these four verticals. So by building a structure like this, we're able to create a tile of 8 qubits. And then if we want to connect multiple tiles of 8 qubits, we create additional couplers to adjacent tiles around it. So this is a schematic of our older processor, the 2000 qubit processor. And in that processor, each qubit was coupled to 6 other qubits. So it had 16-way connectivity. Since we are interested in solving real-world problems, this level of connectivity between qubits is a challenge. It's kind of a limiting factor. So in the real world, we have lots of variables at play for any given problem. We have lots of interactions between these variables. Let's say we're scheduling and we have a set of people that we need to schedule or assign to jobs. Well, people might have relationships, shifts might have relationships. A problem can blow up really quickly and become really complex. And more complex problems require having more relationships. So if we only have 6-way connectivity, it becomes challenging to fit real world problems onto our chip. So one thing we've been really focused on is expanding the connectivity on our chip. Oh, there we go. So with Advantage, that's our current processor that we have available, we were able to extend the connectivity from 6 to 15. So here, every qubit can couple to 15 other qubits. So if we look at, one long horizontal qubit here, you'll see that this horizontal qubit is coupled to every overlapping vertical qubit. It's also coupled to the qubits on either end. And then we have what we call an internal coupler, coupling it to the qubit adjacent to it, horizontally adjacent to it. So this was a really big improvement, but still we have a ways to go to realize the level of connectivity that we really want. That being said, we are working on Advantage 2 right now, and Advantage 2 will further improve our coupling connectivity to 20. So each qubit will be coupled to 20 other qubits. And as we continue to expand and iterate on our processors, this connectivity is something that we're paying close attention to and trying to continue to expand. The more connectivity we have, the more kind of complex real-world problems we're able to embed onto our processor. So this is the motivation behind going in that direction. Okay, so you've listened to me talk for a long time. So I'm going to switch my screen share now and open up our recorded lab tour. Give me one moment to do this. Here we go.
And a quick question, Alex, regarding the previous, is it all a 2D structure or expanding into 3D is what Paulina from US asks.
Yeah, so you can think about it, maybe both. So it is a 2D, the graph is a 2D structure. However, when we fabricate the chip, we do use a multi-layer fabrication stack. But yeah, the layout of the chip is essentially still a 2D structure. That's a good question.
Good. Looking forward to the lab tour.
Okay, let's go. Just let me know if the audio doesn't come through.
When you shared screen, please click on in the left bottom, share sound. Let's do it again.
Okay.
Let's just reshare.
Okay.
You click the green share screen button, and then in the left bottom of it, click share sound.
Oh, I see. Ah, nice. Thank you.
Great. And then you can mute or keep yourself unmuted as you wish.
Oh, good idea. I'll mute.
Of processor development at D-Wave Systems. I'm responsible for the processor development group, which involves the design, test, and development and release of the quantum processor that D-Wave makes, which is the underpinning of the quantum computers that we build. Each of these black systems is a quantum computer. Inside that system is a thumbnail-sized quantum processor. In order to operate and develop quantum processors, we require a fairly extreme operating environment, which includes ultra-low temperatures and an ultra-low magnetic environment. And to achieve those, we need a fairly large and sophisticated system. The main room behind us houses the quantum processor, and the data racks in the front hold the quantum server, where users can access and program the quantum processor. And the other data racks include the cooling system, which includes pumps and is responsible for the chirping sound you can hear in the background. Inside the room, before we get to the quantum processor, there are many layers of shielding which allow us to create the low noise magnetic environment the chip sits in. If you look inside the data racks, you'll see that they don't contain what you would normally expect. So here we have some scroll pumps, which are mechanical parts associated with pulling vacuum on the fridge inside the room behind. So this is obviously highly unusual for a data rack, but has been integrated so that it wouldn't look out of place in a data center. And in fact, the requirements for running the system are consistent with all the services that would be available in a data center, which would include chilled water and power predominantly. In this rack is the quantum server, which allows users from anywhere in the world to interact with the processor itself. This server is receiving information from users, converting that into the machine language of the processor, and sending that machine language into the room behind, where high precision analog electronics will convert those signals into electrical pulses, which are sent through cables into the refrigerator and down through the cooling system to the ultra low temperature of the processor. It executes its problem, and then data from the processor is returned to the server and returned to the user. And the system is very flexible, and that users can be programming in whatever language they're comfortable with, and interacting with it either with this system in their data center or even here in D-Wave's lab. The quantum bits in our processor store information in the form of little magnetic fields. The 0 and 1 correspond to a little magnetic spin. The controls over the qubits are all in the form of magnetic fields. So the quantum processor is very sensitive to magnetic noise and the magnetic environment that it sits in. In order to keep that magnetic environment really low, as well as support the ultra low temperature that it's operating at, this system behind me has about 16 layers of shielding between where I'm standing and where the chip sits at the center. These black panels are really for aesthetic purposes, and they integrate these data racks with a shielded room, which is the first of those layers of shielding, and is filtering out RF signals. So if you were to stand inside the room and close the door, your cell phone would stop receiving a signal. The fridge itself has a combination of radiation shields as well as magnetic shields, which help support the ultra-low temperature operating environment and achieve the ultra-low magnetic field. Inside the room, we have to keep electromagnetic noise very low. So even things like power outlets aren't allowed because power can be quite noisy without extensive filtering. So inside the room, we have the cooling system, and these are radiation shields. So this is the next layer of shielding inside the room. The chip itself, the quantum processor, is sitting at the bottom of this array of shields. And this is, again, the first of several more layers. Inside these shields is vacuum, which is the insulation of the cooling system. When we want to swap the processor or conduct maintenance on the fridge, we warm the system up, we remove these shields, and then the processor is accessible, as well as all of the internals of the refrigerator.
All right. So that was the lab tour. I'm going to pop back over to the slides now. Also, if any of you are in Vancouver at any point in time and want to come see the lab for real, please feel free to reach out to us. We do coordinate lab tours every now and then, and it is quite cool to talk to a physicist and see this in real life. So yeah, just putting that out there. Okay, so before we wrap up, I did just want to address a couple of anticipated questions. I heard that there was some interest in understanding the differences between annealing and gate. So I wanted to call out some of those differences very explicitly from a foundational perspective, from a scalability perspective, and from a use case perspective. So we've already talked about how quantum annealing is essentially an algorithm. And our quantum annealers implement a class of quantum algorithms. There are a few different kind of quantum annealing based algorithms that you can run on the QPU, but essentially at the heart of it, the QPU it implements an algorithm. It is an analog system, so it continuously moves between a transverse field that is acting in the sigma x direction and a user-defined Hamiltonian that's acting in the sigma z direction. So users can interact with sigma z, but they can't interact with other operations or areas of the block sphere. So this is quite different than the gate model, where as a gate model user, what you're doing is defining an algorithm and implementing an algorithm that's running on the gate model quantum computer. So when you're building an algorithm, you're thinking about how to perform operations on the block sphere to manipulate your quantum data in a way that will answer the question that you're trying to pose. From a scalability perspective, I mean, one of the reasons that we chose to start with quantum annealing was also that we did see a path towards scalability, and it was much easier to scale. You know, there are kind of less moving parts, there are fewer noise sources, and noise just looks different on a quantum annealer compared to a gate model quantum computer. For us, the primary sources of noise are intrinsic to the materials that we use to fabricate the processor, so they're flux and charge noise. However, it doesn't always impact the ability, well, it doesn't impact at all the ability to perform an anneal. And there are kind of tricks and techniques we can use to minimize the impact of noise on the anneal for you know, problems that may be impacted by that. So for this reason, we say that quantum annealing is naturally fault tolerant in that we can always perform the algorithm, and regardless of whether or not we get the optimal solution out, even if we don't, we're still getting some information about the solution space to our problem. We're just getting a different sample. With gate, it's much more difficult to fabricate and to scale gate model processors. As we've seen, there's a huge effort from many different organizations on this right now. In order to do so, we need fully error-corrected systems, or we need really smart kind of error correction algorithms. So this is a really active area of research and is one of the barriers or hurdles that need to be overcome to be able to scale the gate model systems to the size that we need to address industry problems. In terms of use cases, we also view annealing and gate as being applicable to kind of different problem types. So with annealing, we talked a lot about how the annealing algorithm is well suited to optimization problems and why that is. Earlier on, we also talked about a few different material simulations and phase transition simulations that we were able to perform on our quantum annealer. So we can use the quantum annealer for both optimization problems and simulations. However, the types of simulations that we can perform are much more specific and need to be more closely tied to a transverse field Ising model than the gate model, for example. So with gate quantum computers, we anticipate there being lots of applications in searching, in material science, in quantum chemistry, and drug discovery. So there are certain types of problems that are classically very computationally difficult. And it's those problems where having access to the entire block sphere and being able to perform many complex operations on that block sphere could, at least theoretically, has the potential to speed up our computation in these problem areas. So those problem areas are not areas that quantum annealing will apply to, at least not in the same way that gate does. And gate model can also simulate different types of quantum systems. So again, we do view these two technologies as very complementary. That is why we're investing in building both. And I'm just anticipating a question or two on solving optimization problems with the gate model. So I do want to address quickly the differences between quantum annealing and QAOA, or the quantum approximate optimization algorithm, which is a gate model algorithm to solve optimization problems. So the way this algorithm works is similar to quantum annealing, we have two different Hamiltonians. In QAOA language, we have a driver Hamiltonian. So this is similar to the transverse field Hamiltonian that we have in the quantum annealer. And its purpose is to kind of introduce quantum effects or mix things up. We also have a problem Hamiltonian that represents the optimization problem we're trying to solve. And with QAOA, what we do is we prepare a quantum state. We apply one of the Hamiltonians. I think we start by applying the driver. We allow the system to evolve under the driver for some period of time. And then we quickly turn that off and turn the problem Hamiltonian on and allow the system to evolve under the problem Hamiltonian for some amount of time. We keep mixing the quantum state between the driver and the problem Hamiltonian. So we're going back and forth between applying one or the other of these. And we do that for a set amount of discrete iterations. So essentially at the heart of it, QAOA is trying to approximate quantum annealing, but deciding how many times to switch between your driver and your problem Hamiltonian and how long to allow the system to evolve under each Hamiltonian is also an NP hard problem. So there is some overhead to QAOA that makes using QAOA difficult for optimization problems. Additionally, we found in the literature that experiments that look at optimization problems on our system and various other gate model systems seem to consistently show that our system outperforms QAOA, both in terms of the time it takes to arrive at a solution and in terms of the quality of the solution. So for solution quality, we look at the probability of sampling from the ground state of this problem Hamiltonian. And in our system, at least in the literature that's out there so far, the probability of sampling from the ground state is typically greater than 90%. Whereas with gate model or QAOA on different gate model quantum computers, this probability ranges from 0.01% to 80%. Is really dependent on the input itself, and it's also highly dependent on the hardware. So we'll see over time, but so far what the experiments and literature are showing is that it looks like quantum annealing will be maybe better suited for optimization problems, just generally speaking, compared to QAOA. And I did include in a couple slides a few more references that explore that question. So we'll send these slides out later, so you'll have access to all of the papers and all of the references that we've covered and that are still to come. Okay, so just a quick recap, because I know we covered a lot. So there are just kind of a few main points that I'm hoping you'll take away from this. Of course, I want you to understand the technology and what we've talked about, but beyond that, D-Wave is the only quantum annealing provider. Our current Advantage system has over 5,000 qubits. Our next Advantage system, Advantage 2, we're scaling up the number of qubits to 7,000, but also we're improving the connectivity. Since 2011, we've shown many different demonstrations of quantum effects in our processor, and we've shown material simulations that show a significant speed up on the QPU compared to the best known classical heuristics. We believe that quantum annealing will likely always be the best quantum technology for solving optimization problems based on the literature that's available today and the experiments that have been done up until today. And last but not least, this is a nice segue into what you'll be talking about tomorrow. D-Wave supports quantum hybrid production applications today, and we've tried to make it really easy to use our systems, to formulate problems for our systems, and to kind of analyze and improve the quality of results that you get from our systems. So all of that is to come tomorrow with Catherine. And here are some additional resources. So here are a few papers on quantum annealing versus QAOA. Also, I've included a link in case you want to sign up for LEAP. It's free. You get a minute of QPU time, so you're welcome to follow along with Catherine tomorrow or explore and learn yourself after. We have a lot of other applications beyond what I mentioned today listed on our page here. And then we have additional resources as well if you want to continue to learn about our technology. So with that, I'll open it up for questions now. Thank you so much for your attention and for staying with me for the past hour and a bit.
Amazing presentation, Alex. Thank you so much. Really insightful. Great to see the lab tour. And there are many questions. The first question is a fun one, namely, if we can use a dilution refrigerator to cool to even 10 millikelvin, can I cool my beer in it really fast?
Okay, so that's funny. You know what? We have a couple physicists here who, you're really not supposed to do this, but on a hot day, they'll go to the back and they'll go to the liquid helium dewars and they'll open the valve, and then you get this burst of cold helium come out, and it's a really good way to cool off. That is not sanctioned by D-Wave. It's not something we promote, but yes, the materials used for the dilution refrigerator can also be used for other creative applications. Yes.
Okay, we can cut this out for the recording.
Okay, that sounds good.
There are many more questions. For example, the maximum number of qubits that you mentioned, is that all logical qubits or total qubits, or is that different for quantum annealing? And Gopal asks 7,000 qubits, did D-Wave already break RSA?
Yeah, that's a good question. So cryptography is a gate model application. So our solver or our QPU is not well suited to cracking RSA encryption. You all are fine. Encryption is still secure and good. And yeah, quantum annealing is probably never going to be useful in the cybersecurity space in that way. But the qubit, so the qubits that we're talking about, because they're not universal qubits, so they don't have access to the entire block sphere. When we talk about a qubit versus a logical variable, we're talking about that more in that space between an application problem and how we can fit that application onto our qubits. So our qubits, so if you have a variable in your application problem or your problem domain, it might be possible that you can map that variable directly to one qubit, and then your logical variable maps to a single qubit well. More often though, what we find is because of the problem structure in the real world, we have to take a logical variable and we have to embed it onto the processor. So that means we map one logical variable to a chain of qubits. So that's maybe the analogy there between the logical, to a gate model.
Great. There are also some questions that you partially addressed already, but I will just continue. I hope. Yeah, many people ask, "Oh, can you stay on for a little?" So I hope you have time to continue the discussion. Great. Already quite in the beginning, Varda from India asked, "Can we also simulate molecules like caffeine, which would usually require 164 qubits, or is gate-based more suitable there?"
We have simulated some small molecules. It's been a while since I've looked into that and looked at the electronic structure for small molecules. Catherine, sorry to put you on the spot. Are you more familiar with that literature?
Yeah, I don't, off the top of my head, I can't recall exactly what size of molecule we've been able to simulate. And the research around that is, like Alex mentioned, it is a few years old, so it's not like front of mind for us. But there are resources available. And if you check out that applications page, there are links, papers there. You can search through, and in the resource library as well. You can search through and look for chemistry type problems, and the papers are listed there. So feel free to take a look. Yeah.
And great that you're here, Catherine. Welcome. I would like to continue with one more question for you. Julia from US asks, what about all the parameters in the Ising model? How are they explicitly decided, like H and J? And do the different choices for these initial Hamiltonians give really different results?
Yeah, that's a good question. So the initial Hamiltonian is set. So we decide that we tune all of the parameters in the QPU when we go through our calibration phase. So before we bring a quantum computer online, we kind of calibrate it and tune everything so that the processor acts as a kind of coherent system as much as possible. From a user perspective, the H's and J's, they come from your problem domain. So they're kind of separate from the way you, well, for the most part, they're separate from the way you interact with the QPU. They define the problem. There are additional parameters on the QPU though, that you can tune. So we looked at the anneal schedule. You can modify how the anneal schedule unfolds. You can introduce things like pauses. You can start from an initial state at the end of your anneal, and you can reverse anneal and then come back. So there you're defining parameters like, what does your anneal schedule look like? So there are more advanced parameters that a user can tune. However, we have kind of calibrated our system so that for as many problems as possible, we're kind of starting at a good baseline, and all you need to do is come up with the H's and the J's from your problem domain. And then yes, you have to tune things like a chain strength. But yeah, we've tried to create as minimal of a lift from the user perspective as possible to use the QPU.
Great. Then Otmane from Morocco asks, following the QML workshop yesterday by Sanadu, is there an application of quantum machine learning using quantum annealers?
Yeah, that's kind of an experimental area. So we have used the hybrid solvers for feature selection. So not directly part of the machine learning workflow, but adjacent to it. There has been some experimental work on classification and support vector machines, and maybe some others as well in the machine learning space, but we tend to see the QPU and the hybrid solvers used for purely optimization problems more so than quantum machine learning.
Yeah. And then more people ask, for example, Durjesh from India, how come you can build 5,000 qubits, but the others can't?
Yeah, they're different than the gate model qubits. So they are easier to build, and they're not fully connected. We're not performing operations on a quantum state. Instead, what we're doing is we're giving the QPU, basically we're giving the QPU a solution space. And we're saying, can you please use quantum dynamics to search through my solution space and find a good answer? So we're not actually performing these like gate operations on our qubits, which is why the requirements for building qubits, scaling them, and using them are easier to meet, I would say, than gate model. Yeah.
And someone asked earlier, if it works so well, why don't others do it? Why don't IBM and Sanadu and Quantinuum do this?
So this is kind of what I was alluding to, or dancing around with the technological milestone slide. The reason that we spent so much time proving and demonstrating that our QPU uses quantum dynamics to solve problems is because for a very long time, at least the academic industry didn't believe that quantum annealing was a real quantum computer. So we've done a ton of work to show, yes, in fact, we do use quantum dynamics in very important and critical ways that differentiate us from any classical processes or algorithms that you might use to solve similar problems. But, it's taken some time to kind of prove to academia that we have a viable quantum computer. And then also at this point, I mean, we've been building these things for over 20 years. So I think the efforts from others have very much been on the universal gate model side, and other modalities as well.
Yeah. Maybe most important is proving it to clients, in which where you have many. And Colleen from the US has a question about it to you, Alex. Alex, with your background in sales engineering, do you see any common characteristics among first customer adopters? Are your clients mostly large established or smaller companies? Any key traits unique to D-Wave?
That's a really good question. Yeah, so in my experience, I've seen kind of 2 or 3 types of customers come by. So that for larger companies, larger organizations, many have innovation teams. And these innovation teams are tasked with exploring new cutting edge technology. So these innovation teams, they love quantum. They come through our door all the time. They want to assess quantum. They want to understand how to apply it to their business. And they often do a lot of work working with the QPU, the hybrid solvers, and their application space. In terms of adoption of quantum, these teams tend to have more challenges kind of pitching this to the business. They evaluate the technology, but they don't necessarily adopt the technology into the organization. What we're seeing, though, is a lot of larger organizations like Johnson & Johnson, Volkswagen, Pattison Food Group, Deloitte, MasterCard, all of these organizations, they want to start exploring quantum now. They have a quantum strategy. They don't want to be left behind. And so kind of from the top down, they're saying, we realize this technology is important to look into, and they're starting to kind of actively go out and evaluate our technology, but also IBM's technology and other hardware providers as well. So yeah, we do tend to see more success with our clients who work directly with a professional services team, because there's a lot that can go into formulation to get good results. And it can also be a lot of work to understand what types of optimization problems, what industry problems or business problems are well suited to our technology. So that's where like Catherine would come in and have these conversations and help clients kind of parse through all of that. I hope I didn't ramble too much.
No, that is really great. And I will field directly the related question from Dawal in India. Dawal says, if I was starting a startup today to work with annealers, what problems should I pick? Do you know of any successful startups that do so?
Yeah. So I don't know if this program is still going on in Canada, but there was a program called CDL, Creative Destruction Labs, and they were essentially an incubator for quantum startup companies. So we used to support that program, and we have a number of relationships that have grown out of that. Maybe the most prominent is with Multiverse. So Multiverse provides financial services to financial services organizations. They have a platform called Singularity where they do portfolio optimization. They use our solvers for portfolio optimization. And they also work with other hardware providers as well. But they're an example of a startup that is built on using quantum for real-world applications.
Regarding the real-world applications, now with the really latest model you're building, the Advantage, what are some problems you're expecting would be easier or finally possible for that quantum annealer to solve? Is what Dunya asks.
Yeah, that's a good question. So in addition to the increased qubit count and connectivity, we're also using a completely new fabrication stack for this processor. And the significance of that is that we are seeing really good early evidence that suggests that it'll drastically reduce the noise, so the intrinsic material noise to our processor. So from a simulations perspective, what this might mean is that it might allow us to extend our coherent quantum annealing research. We might be able to access that coherent regime beyond what we've been able to demonstrate in the work so far, possibly, if we can kind of push out the point at which we start coupling to the environment because we have less noise in the material. So that's one possibility. In terms of customer applications, we're increasing the connectivity, increasing the qubit size. So for the optimization problems that folks explore directly with the QPU, we can support larger problems than we currently can, more connected problems than we currently can. If you're starting to just look into our systems, I would start by looking at some of the more classic graph theory problems, like an independent set, a maximum independent set, maximum cut. These types of problems that have an optimization component on a graph can be a really good way to introduce yourself to the QPU if you're interested in that.
We're gonna play around with some graph problems tomorrow, so
Oh,
we'll see that tomorrow.
Fantastic. Looking forward to that. And then I will just keep on going with questions, Alex and Catherine. Would it be possible to use a different implementation than superconducting circuits? For example, from gate-based models, we know about trapped ions, neutral atoms, photons. Would there be other options here too?
yeah, there are. So superconducting qubits were chosen, superconducting flux qubits were chosen, early on based on the research that was available. Also, though, it turns out that they're easier to fabricate and they're easier to tune. So theoretically, it is possible to build a quantum annealer with different types of qubits, but from a practical and a scalable perspective, we've found and we believe that superconducting flux qubits are the most viable.
Great. Then we also had a bootcamp by Quera using analog neutral atom-based quantum computers. And there is a question, is quantum annealing, does it have some similarities? Because they are also not working fully gate-based. Are you familiar with that? And could you share?
I'm not familiar enough to speak to it in a meaningful way. Catherine, are you?
Not with Quera's implementation, unfortunately. Yeah.
No, and this is definitely very different than quantum annealing. Still a good question. I will continue with a couple of earlier ones. Yes, what is coming up in the future? Because right now D-Wave is working on both quantum annealing and gate models. How do you see the developments? And will we even have some hybrids of those maybe?
Oh, interesting. I don't think we've started thinking about that. Yeah, that's an interesting question. How would you use an annealer and a gate model computer together? I'm going to take that back to our smart research. But the way we kind of see this unfolding, we have a clear, well-defined path in terms of iterating on our quantum annealer. We already have plans for Advantage 3. I was just talking to a physicist yesterday about that. So we kind of know where we're going with the annealers. In terms of the gate model quantum computers, like we are still very, very early on in that stage. So it's going to be a long time. Don't hold your breath to get that in your hands from us. But we do believe that we can leverage a lot of the lessons we've learned, especially on the fabrication side of things, because that is a huge challenge for quantum computing, to hopefully deliver an error-corrected gate model quantum computer. When we're ready to do so, we're hoping to bypass the NISQ era.
Oh.
And I cannot say any more about that.
Yeah,
That's all you get.
Amazing. Yeah, bypassing
From
using quantum annealing.
Yeah. I was going to say, from the application side, I can see situations where having both a quantum annealing process and a gate model process could be beneficial, especially in like the quantum machine learning space. So as Alex mentioned, we have kind of a plugin already for feature selection that uses our quantum annealing technology that could be brought in combination with something like a generative model for the gate-based machine. So there's little ways on the application side that we can definitely like push the two technologies together.
Then to visualize everything a bit more, Artem from Mexico asks, if we run the annealer 1,000 times, would we always get the same result or different results? How much would it vary?
That's a really good question. So, and I didn't mention that. typically when you use the quantum annealer, you do want to run it a number of times, like 1,000, because you do get kind of a distribution of samples. So the reason for that is that, you know, a quantum system is probabilistic in nature. And we saw earlier on in the slides that as we go through this annealing process, the wave function, it delocalizes and then relocalizes. And ideally, we're relocalizing around the global optimum, but that's not always the case. Sometimes we might collapse into a local minima. So we do typically want to anneal a number of times, and then we take the best solution that we got, or the lowest energy sample that we got.
Great. Then a question from Gopal. How do you compare the time complexities of a quantum annealer to the classical solutions?
Yeah, that's difficult. So there are a few different ways. If you're just looking at pure computation time, then you might only compare the pure annealing time to like the classical compute time. Often though, from an industry perspective, when we're working with clients, they're interested in overall, how much time do I need to wait to get a solution? So really, whether it's classical or quantum, from an industry perspective, we're typically looking at all of the overhead combined, and we're usually comparing our hybrid solvers and our solutions to some type of classical heuristic that the clients are using. And they typically have a good understanding of how their algorithm works, how long it takes, what the performance is. And so we would benchmark based on what their needs are and how they want to guide that benchmarking study. But yeah, you're right. There are a lot of different ways that you could approach that.
There are also questions, do you see significant speed ups, and how would you classify that?
Yeah, it depends. It's very problem dependent. So if a problem is a good fit for especially our hybrid quantum technology, then we do have instances where we've seen significant speed up, like CaixaBank saw a speed up of 90% using our systems compared to a classical alternative. But yeah, this is still an open area of research, and it is highly problem dependent.
Then Colleen had another question, also related to time, but differently. Would you apply quantum annealing consistently when you have optimization problems that have changing data, data changing with time?
Yeah, so that's how. Let me see, where is that? Oh my, this is way back. So in one of our studies, we're getting there. Oh my goodness, there we go. Okay. So actually in the scaling advantage over Monte Carlo paper, here, that's what we did. So we started by initializing our quantum system into a state that had topological obstruction. And we did that on both the QPU and on the quantum Monte Carlo simulation. And then on the QPU, what we did is we kind of reran the simulation at different time steps to simulate how that system was settling into an equilibrium state. And, you know, again, we did similar idea with quantum Monte Carlo. What we found is that we were able to much more quickly simulate the settlement of the system into equilibrium, but we were rerunning the simulation at discrete time steps with changing data to get there. Yeah.
Amazing, very clear. Then Durjesh from India asks, how can we join you? What are the requirements? What type of positions are offered at D-Wave?
Oh yeah, so unfortunately we're not hiring now, but we will be again one day. So I don't know, I only have an undergrad and I've been able to move around in a few different areas. Catherine has a PhD, many of our folks have a PhD, but we do try to assess for skills and not necessarily only educational background. So if you do have experience in quantum, whether that's educational or industry, that's really great. if you have experience in optimization, in algorithm development, in more classical computer science, like all of these skill sets are really important, and skill sets that we leverage regularly. So that's where I would start. Also, it's really good if you can use our system and become familiar with our system. We like that when we interview people. Catherine, would you add anything?
No, I think that, yeah, those areas are super important. I think a lot of folks in the quantum computing space recognize that, you know, not everyone comes from like a strict physics background, and you don't always need to be super effective in a quantum computing company. You don't necessarily have to have that exact background. Like Alex said, I have a PhD. My PhD is in mathematics. So a lot of people come from a lot of different areas, which is one of the reasons why I think quantum computing is such a cool field. You get to know so many people with so many diverse backgrounds. Also, like there are also positions in all of the other typical areas for a business, right? Financial analysts, all sorts of different areas where it's helpful to actually be somewhat familiar with the quantum technology space to obtain a position at a quantum computing company. So yeah, that's all I would add.
I would actually piggyback on that with one more thing. I think one big challenge in quantum computing is on the marketing side. So if anyone with a technical background is interested in messaging, positioning technology, marketing strategy, that would be like the ideal mix, I think. So, you know, yeah, just putting that out there.
Great, and thank you for sharing this. Thank you for sharing that all different backgrounds are needed, including marketing, including electrical engineering, computer science, physics, really everything, communication skills, extremely important.
Yeah.
And also there are many PhDs, but Alex, you joined D-Wave without PhD. 2 weeks ago, we had from IQM, Julia joined there right after her master. We had a few more speakers that joined without PhD, so it is not an absolute prerequisite. Great. D-Wave will also be there at the career fair next week, Friday, July 28th. So even when not hiring now, one day, hopefully soon, or maybe for very impressive people, there will be a spot. Catherine, could you share for tomorrow? Can people already prepare something, download some software, make an account?
Sure. Yeah, so Alex had on her very last slide. Oh yeah, absolutely. Alex had on her very last slide a link to sign up for a free Leap account. And in that free Leap account, you get 1 minute of QPU time. So folks that are able to do so, I think you have to be over 18, and we don't have service in all countries. But folks that are able to do so and are interested in following along with what I do tomorrow can certainly sign up for that Leap account. But I'll be going through kind of step by step through a couple of different problems that involve K-graph partitioning. So we'll kind of see that along the way. You don't need to download any software. We have web browser-based support in Leap, and I'll show you how to access that as we kind of go through. But if anybody wants to follow along on their computer, I would sign up for that Leap account.
Great. Valerie asks, will Leap use the actual annealer?
100% it does. Yep.
Excellent. D-Wave is also really important for WOMANIUM right now for the quantum solutions launchpad problems. WOMANIUM is starting a new initiative connecting young talent with companies working on industry projects via WOMANIUM. And already one of the first projects with Deloitte is working with the D-Wave annealer. So we look forward to many more projects using quantum annealing. I will continue if you still have time.
Yeah,
with
sure.
a few more questions. Thanks so much for asking so good questions, everyone. A question from Valerie. Do you work daily in the labs? Do the labs run 24 hours? Are they local to your offices or distance? And she shares great presentation, very informative.
No, I think, yeah. So our lab is just on the other side of the building that I'm in now. So that's located in Burnaby. Our production quantum computers, they are running all the time. We have 24/7 monitoring. We have teams on call 24/7 in case anything happens or goes wrong. We're always ready to respond. We also have a system in Germany and at ISI in California as well. So we're starting to branch out and have LEAP nodes distributed. So not just in Burnaby, but yeah. We do all of our experimental kind of research and our materials and processor development here, though, in Burnaby.
Wonderful. Then Ron from Chicago asks, how is the LEAP runtime allotted?
So if you're using the QPU directly, there is kind of a fixed time for programming the qubits, for doing the anneal based on the number of samples that you're doing, and then for reading out. And there are a few other steps in there too, like a thermalization delay, and yeah, a few other elements that go into that. But it is kind of a fixed time if you're using the QPU directly. If you're using the hybrid solvers, you can specify how long you want the problem to run for. And regardless of what you're using, when you submit your problem to LEAP, it goes into a queue with other problems, and then we service it as quickly as possible. Yeah, and so usually, you know, the delay on that, I was looking at the data a few months ago. For the QPU, it's usually like under a couple seconds, the delay to use the QPU. And then for the hybrid solvers, the delay can range from like 2 seconds up to 16 on average. So it is pretty quick either way.
Great. I will ask one last interesting question from Otmane in Morocco. Can you use a quantum annealer to optimize the gate model?
That's an interesting question. I don't know.
Okay.
I have no idea how you would even start thinking about that.
I'll provide a smart answer to that. Tomorrow, we're going to see an example of distributed computing. So if you had an algorithm that you need to split up over multiple gate model machines, you could use the quantum annealer to do that splitting by setting up a K-graph partitioning problem, which we'll see tomorrow.
Nice
Amazing.
save and good plug, Catherine.
David says, D-Wave can optimize anything you can think about. Okay, let's then save any further questions for tomorrow, or if you think of anything, we will just put them in the channel and we will start with it tomorrow before Catherine's session. Really amazing talk. Thank you for the lab tour. Thank you for sharing all insights and for this extensive Q&A. Really great. So great having you, Alex. Great having you, Catherine, and really looking forward to tomorrow as well.
Yeah, thank you so much. Thanks everyone for your engagement. It was fun. Yeah.
Thank you. Great session. Have a great rest of the day.
You too.
Bye-bye.
Then I will share my screen and give a summary of what we had and what is coming up. So here we go. We started earlier today with a virtual office hour by CQ Tech. This was a question and answer for Q-Nickel. We have a couple of days left to finish the Q-Nickel module, also the QKD module. So please focus on that the next days. Ask all the questions on Discord, and Hussein will give one last office hour on Sunday. Stay tuned for that. Now we just finished the hardware lecture and virtual lab tour by D-Wave. And in a couple of minutes, I think we will take a brief break. We will start the career training by the WOMANIUM founders, how to pitch yourself, and resume training.